Hi guys, I am back. There's one more thing I wanted to go over with you real quick at the end of Chapter 7, and that is something called organic synthesis, also known as retrosynthetic analysis if you want to sound fancy schmancy. Uh, Basically, organic synthesis is going to be something that's going to be with you for the rest of the year and not going to sugarcoat it. This is what many students find to be the most difficult part of organic. Probably that and a certain type of spectroscopy. However, it is going to be a part of life from now on. So what I like to do is I like to try to get this going sort of piece by piece and make it, we start off kind of simple and then build from there. Basically what organic synthesis is kind of doing some of these problems backwards, right? You're used to being presented with, a set of reagents, a set of reactants, and figuring out what a product is, right? In organic synthesis, what you're doing is you're given a target product and you're charged with figuring out a way to make it, all right? Doesn't sound too bad, and honestly at first it's not. It's pretty easy. However, you're going to see as we go on throughout the year is that as we get to more and more advanced chemistry, it will take more and more steps to make an organic product. So for instance, the ones we're going to be looking at right now are pretty simple, right? You guys are just starting to learn reactions, so there's not a whole lot we can put in synthesis. You get into organic 2, though, deep in the year, and you might be having to work backwards to figure out, 7 or 8 steps, right? Don't let that scare you off, though. It's entirely doable. It just takes a lot of work. I actually kind of like it, because I always think that's kind of a logic, puzzle type of thing, but then again, I'm a weird person, so perhaps you don't want to listen to me. Anywho, all right, well, let's take a look at what we're talking about here. And like I said, we're kind of limited right now because you guys haven't learned a whole lot of reactions, but you can sort of see it in action, all right? So let's say we're doing something like this. Let's say you're given a mission to make this compound, okay? And you can make it using any reagents and other materials at your disposal, right? Okay. Well, what you have to do is you sort of have to look at this and you have to figure out, okay, what piece do I need to have here to add to another piece to get to this product, right? For right now, since we're just dealing with Chapter 7 reactions, all of these are going to be basically just one-step reactions, right? So that makes it kind of easy, right? So what I like to do, and there's different ways to approach this, I always like to encourage you to take stock of what you're given as far as the information, right? We know that this particular guy right here is our target product. So let's take a look at it. Let's see if we can figure out what's kind of unique about it, all right? This has an SH group, all right? That's called a thiol group, right? And one thing that's useful to know about this is, what is a thiol group used for? Where do you see it? All right. You should have seen in one of your tables in Chapter 7, SH minus groups pop up on nucleophile charts. All right. So, the thiol group is a common nucleophile. All right. So, if we could somehow take a compound of some sort and there we go, sorry about that. And we could somehow substitute this group on to this carbon, then we'd be in business, all right? We could do nucleophilic substitution, all right? Well, in order to do that, number one, we're going to need a nucleophile, and we're going to need something over here that's going to contain a leaving group, all right? Well, what are some good leaving groups? Well, hopefully you guys have been paying attention this chapter. You guys know that halides are good leaving groups, right? So, one place for me to start would be to maybe say, okay, well, if we had this, let's say an alkyl chloride, right? If we had something like that, then we'd have a readily made leaving group, that's Cl minus, where that could leave where another group with this SH could come in. All right, so this is where I'm going to start. If we take a look at this, What type of alkyl halide is this? Hopefully you're able to recognize this as a primary alkyl halide. What type of alkyl halide, or what type of reactions do alkyl halides like to be involved in? All right. Hopefully you guys remembered that primary alkyl halides only react in this chapter via SN2 reactions. All right. So this is telling you this is an SN2 reaction. All right. What type of nucleophiles work best with SN2 reactions? You go back, you look, and say, okay, strong nucleophiles. So what's a good way for me to have a strong nucleophile that's a source of SH? Well, we learned that sodium and potassium salts are excellent sources of strong nucleophiles. So basically you could take something like this, sodium thiol. It dissociates to give you Na+, which we don't care about, but more importantly it gives you SH-. So that is a strong nucleophile. By the way, you may hear my dogs barking in the background. I apologize in advance for that. Alright, there's one more component to this we're going to need, and that's going to be a solvent. Alright, this won't run without a proper solvent. What type of solvent works best in an SN2 reaction? Hopefully you guys know that polar aprotic solvents work best. So just pick out a polar aprotic solvent. I'll use acetone. And voila. That is a nice one-step synthesis that we've outlined for this target product. Alright. Very good. Let's try another one. I hear my dog scratching around on the floor, and I can't see him. And if any of you guys have dogs, especially corgis, you probably know that's not very good. But nothing I can do about it. Let's soldier on. Alright, let's try another one. Let's say, in this case, you're trying to make something like this. Alright, this is an ether. Specifically, it's called ditert-butyl ether. Alright, so this one's interesting because we actually did an ether synthesis in our virtual lab, right? We did Williamson ether synthesis, and we said it proceeded by an SN2 reaction. However, this one's a little bit different because you'll notice that no matter which one of these, these are identical groups, one of these has to be lumped with an oxygen, right? Alright, if you do that, what type of carbon do you have right there? That would be a tertiary carbon, right? If you did it the other way, you'd be looking at this carbon, it'd be still a tertiary, right? This means in order to substitute one of those oxygen tert-butyl groups, we're going to have to be substituting it onto a tertiary carbon, which means we're going to have a tertiary alkyl halide. We'll use something like this. Alright? So, again, kind of think about this here. Alright? We have no choice but to use a tertiary alkyl halide to get one of those groups. What types of mechanisms do tertiary alkyl halides react in? Yeah, they only react in SN1 reactions. So in this case, you need to set it up to so it'll work in an SN1 reaction. All right. So what type? First of all, what are we trying to get on here? We're trying to get another tert-butyl group and an oxygen. All right. So the question is, are we going to use like a sodium or potassium salt here? No, we're not. Because what works best with tertiary alkyl halides and SN1 reactions? Weak nucleophiles. Alright? So if you remember, we talked about before in some examples with SN1 reactions, we saw that water worked great as a nucleophile, as a source for OH. Alcohols work great as weak nucleophiles. Alright? And that's what we're going to use here. We're going to use an alcohol. Alright? So so this is actually, right here. This is a complete synthesis, outline of the synthesis here. Because we also learned that in SN1 reactions, the nucleophile actually doubles as the solvent quite frequently. We need a polar protic solvent. This alcohol, tert-butanol, would work well as the solvent as well. So this is a synthesis here. All right. If you're wondering how it would work, just to refresh you, basically what's going to happen is that's going to act as a leaving group. You have a carbocation. Your tert-butanol acts as a nucleophile. It attacks. And then you get a deprotonation, and then boom, you have your product. By the way, the mechanism is not necessary when I say outline a synthesis. You don't have to write the mechanism unless I specifically ask for it. But, I just wanted to put it in there so you could see. All right. So what's interesting about these syntheses is that sometimes you have to do an SN2 reaction. Sometimes you have to do an SN1. Other times you might be okay either way. Let's say I tweaked that one a little bit. Instead of making ditert-butyl ether, let's say that we were making, diisopropyl ether instead. All right? Now the big difference here is if you lump the oxygen with one of these, what type of carbon is this one? That's a secondary carbon, right? So that means you would probably need to start off with a secondary alkyl halide. Now, what type of reactions can secondary alkyl halides undergo? Yeah, they can do either one. They can do an SN2 or SN1. So you would actually have a couple of correct possible pathways here. If you wanted to say SN2, you could, set it up as an SN2 reaction where you had this. You had a strong nucleophile, something like this, as a source of your nucleophile, where this would come in, knock that off, and give you your product. Come on, whoops. All right, since it's SN2, you would need a separate solvent, a polar aprotic solvent, excuse me. Just so I don't end up using the same one every time, I'll just toss out DMSO as a fun little option. So that would be a possibility. Or you could choose to do this as an SN1 reaction. All right, in this case, instead of having, an ion, a sodium salt from an ion, you could just put in a covalent compound like this that would serve as a weak nucleophile. Could also double as the solvent, and then you guys can map out the mechanism since I'm running out of room. There. So in this case, there would actually be a couple of different correct pathways. And that's something that's, some people like about synthesis and other people hate. Frequently, there's actually more than one correct pathway. Some people don't like that because, you almost get, frustrated by having too much freedom. Some people just want one correct answer, but other times it gives you some versatility. That being said, we are going to learn later on, there are some considerations you have to make, right? Technically, either one of those is a correct synthesis. I can tell you, only one of them would be practical. But if you put either one of those answers at this point, I would be perfectly fine with it. Okay? Let's try one more. Let's try something like this. Let's put a little stereochemistry into it. Alright. Put a couple of methyl groups down there. And, whoops, that's a stray line. Shouldn't be there. Oh, son of a nutcracker. Come on. Let's put an OH group here. Alright, so this is our target. By the way, the reason I didn't put dash wedges on those two methyl groups is because that is not a stereogenic carbon, right? So I don't have to. I could have, but it doesn't really matter. Here, The important part is this OH. All right, so let's say we're doing a synthesis here to get this compound and only this. No others. All right, that's important because we're going to see here. Let's look at this carbon that the OH is attached to. What type of carbon is that? That's a secondary carbon, right? So you're thinking, okay, if this is a secondary carbon, maybe we could do either SN1 or SN2 to get this, right? But the stereochemistry should give you a little bit of a clue, right? We only want one particular stereoisomer. We don't want any of this. It's really sloppy, sorry. We don't want any of that, though. We just want the other one. Okay, that's important because if you remember, when we did substitutions at stereogenic centers, one of the mechanisms always gave us a single stereoisomer. The other one always gave us a racemic mix. Hold on one second. My dog is whimpering to get out of the room, so I better do it before he starts grumbling real loud. Okay, Dipper, come on. No, you cannot have the toy. Come on, Dipper. Okay, sorry for that delay. Corgis are really temperamental dogs, by the way. They're super fun. They're super derpy, too. But he's also not very patient, so he was going to start making some noise. All right, anyway. Yeah, we want the one that only gives one stereoisomer. And that is going to be an SN2 reaction. So we want to set this up to be an SN2 reaction. All right? All right, so what would be a good nucleophile to give you OH? Well, we want a strong nucleophile, so, using a sodium salt or potassium salt, just use potassium, just be different here. Something to give us OH minus. Okay? We were going to want a polar aprotic solvent. Let's use THF here, just for funsies. All right, and then we need an alkyl halide. Now, you want to think about this. Why do we only get one stereoisomer with SN2 reactions? Reason is, if you remember, we always get complete inversion of configuration because we always get backside attack. That means your leaving group, in this case, should specifically be on, we'll use iodide here, should specifically be on a dash, right? If this is an SN2 reaction, the OH is coming from the backside of the iodide as it leaves, then the OH must be pointed in the wedge direction. Okay? So these are the kind of things that you think about whenever you're doing synthetic reactions here, or synthetic pathways. You got to figure out some of these little nuances. All right, so like I said, these are pretty simple now. They will get more complicated, but we'll be doing it brick by brick, right? As we go along, we'll get a little bit harder, so you guys should be able to work up to them. All right, that is all for now, and that is all for Chapter 7. All right, hope you guys have a good night. See you later.